So we start a new section, a new chapter on refrigeration and heat pump cycles or systems. We're going to first go back and take a look, just like we did when we started vapor power cycles. We went back to the Carnot cycle. For refrigeration, here's just a big box, let's call it our system that's undergoing refrigeration. You have to supply either a work or a power to it. And what's the goal? Well, you have it in the presence of a low temperature reservoir, and you have it in the presence of a high temperature reservoir, and the goal is to pump heat out of, or generate a heat transfer out of that low. So it could either be just like this is either amount of work or a rate of work. You could have an amount of heat transfer or a rate of heat transfer out of that low temperature, and then you're going to have to dump it, aren't you? You're going to have to dump it. So you either talk about an amount that's dumped to the high temperature reservoir or a rate at which it's dumped. Either one works. So how does that system work? What's inside this box that makes it work? Well, these are the common components that are inside the box. One is a compressor that intakes some substance and compresses it. Now, if the substance was a liquid, we would call it a pump. But the purpose of the pump and the purpose of the compressor are the same, to boost the pressure. So what comes out of the pump, or the compressor in this case, because you're going to ingest something that is not a liquid. It's going to have some vapor, if not a bunch of vapor in it. You're going to put it into what we call a condenser. So what exactly is a condenser? Heat exchanger. It's a heat exchanger. The purpose is to transfer heat out of it. It's going to end up condensing the refrigerant, that's the working fluid that's flowing through the compressor, through the condenser. And so if it's going to be transferring heat out of it, what's the direction of the heat transfer? Well, it's going to be like this. And we could talk about the rate of heat transfer out of the working fluid in the condenser per unit mass. We've done it a number of times. This lowercase q is q dot, the rate of heat rejected out of the condenser to the high temperature reservoir, divided by the mass flow rate through. All right. Now, what do you have after the condenser? Well, in the Carnot cycle, you have high pressure, and it's coming out liquid. It's coming out saturated liquid. Well, you're going to drop it to a low pressure. But if you're going to try and do that maximally to get the maximum efficiency, you say, well, I probably could extract a little bit of work out of that. So what we'll do is we'll put that liquid through a device to extract mechanical energy or work out of it. See, we had to feed the compressor. Let's use lowercase wc. So that's kilojoules per kilogram into the compressor. Well, what we'll do is we'll come out. I know we're breaking our sign convention there, both for the compressor. Now, actually, it's good for we break it for the compressor and the condenser, but it's good for the turbine. And it's coming out of the turbine. Where does it go? Well, it helps to feed the compressor. Okay. Now we have low pressure, and we put it through an evaporator. What's the purpose of the evaporator? Evaporate the fluid. When you evaporate a fluid, that's just a heat exchanger. You're going to have to supply heat from the surroundings. Well, the heat comes in from that low temperature, QL, just like this is QH, or sometimes we'll write Q condenser, and down here maybe that's Q evaporator. So you get the perspective of what's happening to the fluid inside of either of those heat exchangers. The evaporator, the fluid's evaporating, going into the vapor phase. It makes sense. And in the condenser, what's happening to the refrigerant? It's going into the liquid phase. It's condensing as it flows through the condenser. I know that can be tricky at times, but go slow as you begin the study here. So let's do a first law analysis for the compressor. You do a first law around it. It's steady state. Really, the compressor is not a heat exchanger. It's just you supply work to it. It changes the enthalpy of the working fluid. So the first law gives us that this is equal to an H going out. We have to number our states, don't we? So let's go ahead and number our states. It's traditional that we'll put 1 is the input to the compressor. State 2 is the output to the compressor, which is the input to the condenser. State 3 and then state 4. All right. So the work going into the compressor will be this enthalpy coming out at 2 minus enthalpy in at 1. Have you written the first law enough times for a device? Does that make sense? Does it agree? All right. How about this? What is the rate of heat transfer going out? The direction is shown in the illustration. Out of the working fluid as it flows through the condenser. It's H what minus H what? H2 minus H3. And then how about for what's going out of the working fluid, out of the device called the turbine? H what minus H what for the turbine? H3 minus H2, correct? And now what is going into the refrigerant?
Do you mean H3 minus H4?
4, you're right. That's 4. And what about going into the evaporator? H1 minus H4. You got to always look at the direction of, okay, am I talking about this heat in or work in or heat out or work out? Okay, but I like to think which enthalpy is higher. H1 is higher than H4. So there you go. So for the Carnot, let's go ahead and sketch this on a temperature entropy diagram. Here's our temperature entropy diagram. It's not perfectly symmetrical, but hey, close enough. Sometimes it has a long tail, maybe as a tightened tail, on either side. But this is just a general illustration of a temperature entropy diagram. And what we would like to do is all of the heat transfer coming out of the condenser, the fluid goes and stays at the same temperature. So the temperature of the fluid coming in here, we'll call that TH. It's also the temperature going out, TH. It's all at TH. Even though there's heat transfer out of the refrigerant, it maintains its same temperature, TH. First time students see that, they say it's impossible. But you passed Thermo 1. It's not impossible, it's possible. You mean you can cool something and it not change its temperature? Yes. How? Because of the latent heat, because of the phase change. So everywhere in that condenser, it needs to be changing phase. So if we think about it, we have a high pressure side, which is the condenser side. If I just cut this in half, everything over here is the pressure is high. And everything below, on the evaporator side, the pressure is low. So we'll talk about the condenser pressure. That's the same pressure which is the input to the output. It's a high pressure. And we want that refrigerant to change phase at the same temperature. So we put a line of constant pressure, high pressure. And the maximum we can get would be, well, it's going to come in right here at state 2. We saturated vapor, and going out at state 1, saturated liquid. Not 1, that's 3, isn't it? Get the right numbering here, 3. Does that make sense? How about for the low pressure? So this is the high pressure. We draw a line of low pressure, pressure low, and we say, okay, well, we're going to be evaporating all at the same low temperature, at the same TL, just like we condensed all at the same TH. So now we have to just figure out where are the locations of state 1 and state 4. Now, it's not too hard, but let me give you some options. Is state 1 here or is state 1 here? Where is state 1? Now remember, what diagram are we plotting? The temperature entropy diagram. So the key is on the x-axis, isn't it? So if we put it through the perfect compressor, there's no heat transfer. It's reversible compression. What is the relationship between S1 going in and S1 going out of that compressor? They're the same. So don't be tricked. Don't put it there. You put state 1 right below state 2. So it's a little funny because we think first about fixing where state 2 and 3 are on our temperature entropy diagram, and then that tells us where 1 and 4 are. Guess where 1 is? Directly below 2. Guess where 4 is? Directly below 3. And so when we sketch the cycle on a temperature entropy diagram, it just becomes a box, a rectangle. So all of the heat transfer going in at the low temperature happens at TL. That's the Q coming in the evaporator. All the heat is transferred out, Q in the condenser. We have work coming in the turbine, and we have work coming out, depending if you want to show it that way or one way or the other. Let's show it kind of out this way. Out of the, whoops, that was a compressor, wasn't it? This is out of the turbine. And we know how to calculate it. So, same strategy as what we had when we were introduced to the vapor power cycles and gas power cycles. Make a table of properties for all the states. Make a table of all of the major heat and work transfers for the major components. So let's go ahead and make a table of our properties. So let's talk about state 1, 2, 3, 4. Those are our major states. And we have the pressure in kilopascal, temperature maybe degrees C. I would also put for the first time through a temperature in Kelvin. It's an easy conversion, just add 273, right? But I would put it there anyway. I'd talk about the quality. I would talk about the enthalpy in kilojoules per kilogram, and I'd talk about the entropy in kilojoules per kilogram Kelvin. And then I like to put an extra little column over here. It's how I fix the state. A little note to myself. A little note to myself. And there's state 1, there's state 2, there's 3, and then 4. Now, this is what I would do, is I would first focus on state 2. State 2. What was some information, a note to myself to help me fix state 2? Typically given in the problem, they'll give us the pressure of the condenser. And the other piece of information to help us fix the state is that it is saturated vapor. So it's saturated vapor. Once I know, oh, it's a high pressure and saturated vapor, I've got it. Sometimes they'll give us the temperature instead of the pressure for the fluid in the condenser. That's okay. So now let's say that they give me the pressure. I put the pressure here and it's saturated vapor. So what is H? H of G at that pressure. What is S? S of G at that pressure. What is the quality? 1. What is the temperature? T sat at that pressure, isn't it? Okay. Now let's go do state 3. What do we know? It's the same pressure, isn't it? It's the condenser pressure, the high pressure. And what else do we know? It's saturated liquid, saturated liquid. So we know this pressure, and we know it's saturated liquid, so H is F, saturated liquid enthalpy, and S of F, the quality is 0. And what about the temperature? And the key is these are the same, and these are the same, aren't they? So the temperature at state 2 is the same as the temperature at state 3. Okay, now that we have those two, now let's focus maybe on what I would say the more difficult or challenging. What about state 1? State 1. What do we know about state 1? That low pressure and that it's isentropic, so it's the entropy fixes the state. So pressure and entropy fix the state. And so S1 is equal to S2. Sometimes I just write an arrow like this. I say, look at that. That's what I know. I know S at state 1. How? Well, conceptually, I did a second law analysis. There's no heat transfer. There's no irreversibility. It's a perfect compressor. Boom. Isentropic compression. And what about this pressure? Well, this is the high pressure, and the high pressure, this is the low pressure in the evaporator. So how do I find the enthalpy and the temperature for state 1? How about the temperature at state 1? What would it be equal to? Look at the TS diagram. It's the saturation temperature at that low pressure. So it's Tsat at that pressure. Then what I would do is typically I would do it in a two-step process. I would get X first. What was X? The quality. I'd calculate the quality at state 1 first. So what's the equation for the quality at state 1? How am I going to first get the quality at state 1? S1 minus S of F divided by Sg minus S of F, based on the entropy. Now I have the quality at state 1. How do I count the enthalpy at state 1? H of F plus the quality times H of G minus H of F. The quality is just that mass fraction of the substance in the two-phase mixture, which is in the vapor state. That's all it is. And so we use it both for the entropy and as well as the enthalpy. Does that make sense? That's how you get that state 1. If you got state 1, state 4 is just as easy. So what is the pressure? It's the low pressure. Well, I should say it's pressure and entropy fix state 4 from state 3. So S4 is equal to S3. Sometimes I just put an arrow, say that's the same S. And then I say, okay, that PL, that's the same as state 1. And that saturation temperature, Tsat, that's the same. And the quality, X4, is figured out the same way. Here I'll write the equation. X4 is equal to S4 minus SF at that pressure of 4 divided by Sg minus SF. Maybe I should have put S1 right there. And then I get the H4 just like this too. So H4 is equal to H of F plus the quality at 4. I should have put a quality at 1 right there. Times Hg minus Hf. Once I populate my table for the states and all the properties, the most important is going to be those enthalpies, because the enthalpies allow me to calculate the Q's and the W's for the major components. So I'm out of room, but I need to scoot down a little bit to finish this off. All right, so we'll make a table of the component, and we'll call the first component the compressor. And we'll talk about the heat transfer, kilojoules per kilogram, and the work transfer, kilojoules per kilogram for that compressor. And so for the compressor, it's no heat transfer. And we already did it. It's going to be the H2 minus H1. The next component will be the condenser. And it's all heat transfer, no work transfer. And it's going to be the H2 minus H3. And notice that's out. We like to work with positives. If you want, for the cycle, you want that to be into that, then you just switch the signs. Okay? All right. I need to scoot down more. Sorry about that. How about this turbine? Well, there's no heat transfer. It's enthalpy H3 minus H4. That's the work out. And then the last would be the evaporator. Well, all of it's the heat transfer and it's in, so it's H1 minus H4 and 0. Again, which one of these do we expect to be negative? This term from our typical should be, we treat it as positive, but we remember it's work not out of the turbine, but into. I'm sorry, not out of the compressor, but into. So it's into the compressor. And then this is from or out of the condenser. What would be our metric of interest? Our metric of interest would be a coefficient of performance for the refrigeration cycle. Now, I know the book uses either beta or gamma. I don't. Sorry, I just deviate from the book. It's COP. It's so much easier to remember. Coefficient of performance, COP, instead of, it's gamma for the heat pump and beta for the refrigeration or something like that, right? So here I am. I just deviate from the textbook. I'm up front with you, right? Help you a little bit here. And so you put a COP with the subscript R, and that's the coefficient of performance for the refrigeration cycle. It's what you want, what you desire, over what you had to provide or pay for. What do you desire for a good refrigeration system? What do you want? A large Q into the evaporator. And what do you have to provide? Well, you have to feed work to it, which is the difference between the work that you had to feed the compressor minus the little bit that you get out of the turbine. The net work into the cycle. Okay, so I know we can play with this a little bit. You can put that this is the QL. Is that work net equal to Q net? Sure. Okay, is the Q, I know that let me just do this. There's a couple steps. It's done in the previous chapter. I was going to repeat it here. But what you could do is you can go back and say everything's internally reversible. And the ratio of Q's should turn into a ratio of T's. In that case, the Clausius inequality, but it's an equality when it's internally reversible. And then you can work out that the coefficient of performance for this refrigeration system, for the Carnot refrigeration system, comes in at TL. Let me get rid of this so it's less confusing. Divided by TH minus TL. How many people? Everybody's going to raise their hand now. Remember something like that? Yeah. Right? And we're never ashamed if we have to go back and review something in a previous chapter. So this was introduced when we first had Carnot cycles and we first had the refrigeration and the heat pump. So there you go. Now, what's really interesting is you'll go into the tables and you pull all of these values of H's and S's, you'll make your computations, and you'll be able to calculate the coefficient of performance from all of the work and heat transfers for the different components. And then you'll have a very simple equation. And when you make that calculation using that simple equation, guess what you get? If you did it right, you get the same answer to like 3 or 4 significant digits. Okay? All right. So there's the Carnot. Here's a problem. We have a refrigerant 134A. It's a working fluid in a Carnot cycle. The evaporator temperature is given. So they didn't give us the evaporator pressure, they gave us the evaporator temperature, which is fine. And the saturated vapor enters the condenser at 52 and exits the condenser at 52 degrees C. So they give us the temperatures of the condenser instead of the pressure of the condenser, but that's fine. And the mass flow rate in the loop is 5 kilograms per minute. Determine things like what is the rate of heat transfer to the refrigerant passing through the evaporator. Well, remember, try to put the condenser above, the evaporator below. Try to put the device that increases the pressure on this side. Call that the compressor. And the device that drops the pressure, the turbine, on that side. Because when you then lay out your states like 1, 2, 3, 4, that when you put it on a temperature entropy diagram, the states go 1, 2, 3, 4 in the same type of order. 1, 2, 3, 4. That's why they put them in that way, lay it out. All right, so what we have to do is figure out what is state 2. Sometimes we'll just say this is saturated vapor right there going out of the compressor into the condenser. That's the Carnot assumption. And it's saturated liquid right there. True? Okay. So with numbers now, we just have to start filling out our data. So what is the standard table? So list our state, 1, 2, 3, 4, and then list our pressure and our temperature. Here we're working degree C. So let's not fill up our pressures first. Let's fill up our temperature column. So what about the temperature at state 1? What is its value? Here's state 1 right there. I want to put a number right here in the table. What is that temperature? 4. What's temperature at state 2? 52, 52, and then 4 again. Now, what about our pressures? You just have to go get the table and look up those PSATs at that temperature. Okay. Let me do this in the interest of time. I have it worked out on the next slide. I'm just going to outline again how to calculate it, then I'll jump to the next slide and show the numbers. Okay? But everybody should be able to do that, right? Okay. And then once you have the pressures all figured out, and there's really only 2 pressures, you have the high pressure and the low pressure, and that's it. The high pressure side, the low pressure side. Okay. Then we can talk about the quality. Can we fill out any of these qualities so far? 2 and 3. So it's 1 and 0. Because this was saturated vapor and this is saturated liquid. All right. How about some of the enthalpies and entropies? Well, this is H of G and S of G at that temperature and pressure. And this is H of F and S of F. Okay. Now, can you tell here this state 1 is going to have a relatively higher quality than state 4, isn't it? And just looking at it, I would expect maybe that enthalpy at state 1, I don't know, maybe 80%. How about the enthalpy at state 4? Maybe 20%. And then you would calculate the H's and S's. Let me just show you the solution to this problem because, well, first of all, what do we ask to calculate once we get our pressures, temperatures, enthalpies, entropies, all the properties, and then we get all the Q's and W's for each of the components? We're asked to calculate the rate of heat transfer to the refrigerant passing through the evaporator. So this would be in kilowatts. So this is Q dot in the evaporator. That's equal to the mass flow rate, M dot, of the refrigerant flowing through. That mass flow rate's given as 5 kilograms per minute, so that's the M dot, times the Q in the evaporator, so M dot times the H1 minus the H4. And chase your units, make sure you get kilowatts as the answer. How about the net power into the cycle, W dot net? Well, it's going to be the mass flow rate times what you have to feed to the compressor, that's this part, into the compressor, minus what you get out of the turbine. Is that it? And then those W's are both related to delta H's. And then last, what is the coefficient of performance for that refrigeration heat cycle? Make 2 calculations. Make sure that you calculate it using the simple equation, which is the temperature low divided by temperature high minus temperature low. That's why I like to put a column of those temperatures in Kelvin, because what do we know about these T's that you put in this simple equation? Can you put in degree C? You better not. It has to be an absolute temperature. All right. As well as the coefficient of performance calculated using a ratio of part A and part B, answers to part A and part B. Isn't what we wanted the rate of heat transfer in the evaporator? Isn't that where it's cooling something? And then what is this? The net power having to be supplied to the cycle. And they'll give you exactly the same answer. Let me show you. So here I made the nice illustration, labeled my states, made little notes. Hey, it's saturated vapor, saturated liquid. Then we put the diagram on, the TS diagram, the box numbering our states. And then here is a summary of all of the calculations in an Excel file. So we can see that it's 337.7 kilopascal on the low pressure side, 1,385.1 on the high. Those are the temperatures. Here are the values of the enthalpies and the entropies. Notice you just have two entropies, two S's. And notice the quality. It's around 30%, a little over, and very high quality, 98% at state 1. So if I draw this line is just a graphical illustration, but it's pretty straight coming down like that, such that this location of 1 is close to the saturation temperature, or the saturated value at that temperature. Okay. That's why that quality is so high. Okay. Let's go ahead. We compute our Q's. Notice I went ahead and left all of my Q's positive. I know that when you do Q net, you have to take and subtract 1. True. And so what's being rejected in the condenser is greater than what's being absorbed in the evaporator. And so it's 21 net out of the cycle. The work of the compressor, work of the turbine. So it's a net of 21.96 into the cycle of work. Just opposite of our power cycles. Now, I know I've abandoned the plus and minuses because there would be just a bunch of negatives. Okay? And we get more confused when you have a bunch of negatives. But you calculate the COP using the ratio of this Q in the evaporator divided by the work net. You get about 5.77. Use the simple equation, TL over TH minus TL, when you use Kelvin temperature, and you get to good 3 significant digits, the same COP. That's good to have a confirmation, like, okay, I'm more confident I've done this correctly. And then if you want it in terms of kilowatts as well as a ton of refrigeration, we'll talk about a ton of refrigeration next time. It's just a ratio, but often we specify refrigeration in tons of refrigeration. And then this is the power. So here are the 3 answers that were asked for this problem. Let's take a look at a real plot of the temperature entropy diagram for refrigerant 134A using the data out of our tables. Up here, oh, I forgot the name of that point. Critical point. It's kind of a funny name. But anyway, it's a critical point. So over here is this line of saturated vapor conditions, saturated liquid. All right. So where was our temperature at which the fluid was condensing in the condenser? It was around 52. There's close enough to 52. Boom, there you go. What was the temperature that we, for our problem, had an evaporator? About 4, right? No, this is 20, that's 4, there's 4, close enough. So on to scale, this is to scale. Where is state 2? Where is state 3? Where is state 4? And where is state 1? And what was the quality of 1? Very, very high. It was like 98%. And what was the quality of 4? 30-something percent, 32-something percent. So you can see, oh, that makes sense. So sometimes we get really artistic in our temperature entropy diagrams. We just make them pretty symmetrical. But a lot of fluids are not. They're pretty steep. And this refrigerant right here is fairly steep right in here. Okay? So why is the Carnot refrigeration cycle not practical? Why don't I call up the vendors that are making these things and say, no, don't give me your traditional. I want the high performance. Give me the Carnot version. Okay. Well, first of all, they're not going to understand your question. But there's two reasons why this is not practical. Can you tell me at least one of them? Or give me one of them, and then we'll go to the second one. Okay, let's say that we can get pretty good at making a compressor such that it's not necessarily irreversibilities like friction. We can minimize the friction. That's a good one, that's a real one, but I'm thinking of something else. Give me another one.
But the condenser can go with the same T and go out with the same T.
Actually, the condenser could do a pretty good job. If I fed it saturated vapor, it would come out with saturated liquid at constant pressure. That would be okay. Somebody else. Somebody says, okay, I want you to go and build each of these components or purchase them. Okay, do you think you could do a pretty good job of building and designing and building a condenser? It's just a heat exchanger. How about an evaporator? It's just a heat exchanger. How about a compressor? How about this turbine? Look at the inputs and outputs of both of those compressors and turbines. What do you got?
Might be remembering wrong, but I thought the turbines don't work with saturated liquid.
Yeah, so what's coming into this is saturated liquid. What's coming out of that turbine, we just talked about it. Is it compressed liquid? Superheated vapor? No, it had a 30% quality. What's coming out of that turbine is a two-phase mixture of liquid and vapor. Okay, let's talk about the pressure. Looks okay. When in high pressure goes out low pressure. That makes sense. Let's talk about the temperature as well as the condition of the fluid going in and out. We just talked about liquids and then coming out two-phase. That's going to be very challenging. Let's talk about the temperature. Did it come in cold and go out hot? Or did it go in warm and come out warm? Or hot and come out cold? What did it do for the temperature? It came in hot and went out very cold. This is not an easy. There's no turbine like this. It doesn't exist. You can't buy one. If you want to be a stellar engineer, go design one. But oh, by the way, you better compare. What we're going to do is we're going to replace it by something very simple that works, that's very easy to manufacture, very robust. It's just an expansion valve, okay? So it drops the pressure. And even you can make the comparison of, I put in a perfect turbine, if I could design and build one like this, and it wouldn't improve the performance that much. Test me on that. Check it out. Because how much work did you actually get out for this example of that turbine? Yeah, you got some out, but it wasn't enough to kind of match what was going into the compressor. Okay, well, let's jump over here. There's one other thing. So this turbine is the big Achilles heel for sure. Doesn't exist, can't buy one, and don't want to design and try and build it. What's the next one? It's about the compressor. What type of compressors do you like to buy? What do they like to ingest into them? What do they not like to ingest into a compressor? They do not want any liquids. No liquids. No fraction of liquids in the mixture going into it. So they want vapor to go in or gases to go into a compressor. So those are the two things. The turbine expands from saturated liquid to two-phase liquid-vapor mixture. Very hard to do. You want to do a senior design project? Go for it. And then you want a compressor. You don't want one that has to intake two-phase liquid vapor. So what do we do to modify to get away from Carnot? We switch this to saturated vapor down here. We leave this saturated liquid, and we put right here a very simple device, expansion valve, and that'll be our vapor compression refrigeration system that we study next time. Thanks for your attention. I'll pass back your exams now.